Hi everybody. I will try to start a stream. So the idea of this stream would be to record a bit of some electronic design, and maybe later to create some cut of this stream. So the project I will be working on is I called it CleverHand. So the idea is to create a device that is modular, wearable, and that is able to record EMG signal from a subject. So it can be on the arms, on the shoulders. It can be anywhere on the body. And the idea is that currently there are different the state of this EMG. Let me open. The state of the EMG market, let's say, is a bit sad because there used to be the Myoband. Myoband was a very cool product that was, I think, owned by Amazon at some point and then sold because it was not bringing in enough money, and then bought again by a startup, and then now it's owned by Meta. So yes, here you can see what it looked like. So the idea was really cool. It's 8 electrodes that are bipolar. So you have on each face of the electrodes, you have on each module you have 2 electrodes and one ground in the middle. And what was really nice, so the fact that it is super easy to put on the arm of the user, of the subject, and you were able to record some muscle activity from there, and it was very affordable. It was, I think, €200, something around that. So a lot of researchers started to conduct experiment with it, but I think that was the issue, is that the only market or the main user were researchers, because in terms of general usage it might not be very useful. The things they were trying to sell it for example, controlling drones for daily life activity, but actually it's not so useful. And the thing is that the technology at this step and let's say the software side was not evolved enough to make really something out of this signal. So yes, so in the end I think the market was not really what they were expecting. Also for example, for prosthesis control, like this for example, the thing is that it was not very easy to put on a amputated arm. So you could put it, for example, on the biceps, but then you would have just two signal from the biceps and the triceps, and maybe not so much action that you could do to control the prosthetics. So yeah, so in the end it didn't work so well in terms of business, and they ceased to develop and to sell this product. And now a lot of researches have been conducted with Myoband, but they cannot anymore. So now I think it started to be few years now that it has stopped, and the devices start to get old, and when the researchers want to replace them, they need to go on Amazon or on eBay to find some reseller, and it is quite expensive, and then it is not worth anymore. You have other type of EMG recording device. For example, there is a company called Biolab, I think, that is selling some type of big devices like this that are able to record a lot of EMG channel, and that is quite precise. However, it is quite expensive, like really expensive. since there is not so many people on the market, and they don't sell, probably not so much, so they sell it super expensively. And in terms of let's say more DIY, you have smaller devices like I think, is it SparkFun? I think SparkFun has a cool device like this, quite affordable. You directly have your 2 electrodes on it. Here you have the ground that you can put somewhere else, and you can buy directly these electrodes, and in a way you could recreate the myoband with this device. You put it on a bracelet, and you can read from maybe 8 different of these electrodes, and it's not so expensive when you look at the price. It's around $40 for one electrode. So I mean, if you need 8 or if you need 10, then it's starting to get a budget. But yeah, let's say that compared to the previous one I just show you the OTBO Lab, for example, that would be more around 1,000 or tens of thousand euro. I think this SparkFun solution is closer to what the DIY community could do, or small research group, for example. So seeing that, I thought, okay, EMG recording seems to be interesting. Let's see how it's working, just the fundamental of EMG recording. So when you look at it, will I have some nice images? EMG, actually, the EMG signal for electromyography is the electrical signal that is propagating all over your limbs, your skin, due to muscle control. So when your brain is sending a nervous impulse to activate a muscle, this nervous communication generates some voltage change over the muscle, but also over the skin and over all the tissue that the nerve goes through. So you can measure actually these voltage differences, and that's what EMG recording is. So you have 2 points on the body, and you measure the voltage at this point and the voltage at this point, and you try to make sense out of this voltage difference. And so you can have something like this. So usually EMG would look like something like this. So here, for example, if you have someone that has a 2 electrode, someone that has the 2 electrodes attached to the biceps, and the person is doing some flexion. So here you have 1 flexion, 2 flexion, 3 flexion. So you have this type of very noisy signal, but still you have some information inside. And the, let's say, standard, very basic processing that you do over this is you do some filtration, because you have a lot of other noise and some frequencies that you don't care. So you remove all of them. Then you do rectification, which means you just put everything in positive. So everything that is here, you put the absolute value and you put it on the other side. Then you do some smoothing, because what is higher frequency, maybe something that is above, I think already most of the thing above 200 hertz, I think most of the usage they dispose of what is above 200 hertz. Doesn't mean that there is nothing interesting, but for most of the application, people would remove anything that is above, let's say, 500 hertz, and also remove the DC signal. So they would do a bandpass filter, removing everything that is below, let's say, 10 hertz, and everything that is above above 500. And after, so you have this signal, and after, if you want to make even easier, let's say, threshold detection, you can get a very low pass filter of this signal to get the envelope of the signal, and know when the person is doing flexion or extension, depending on which muscle you are recording. So yes, so that's the basic, and so in a way it's not so complicated to do, because you just need some quite precise amplifier that is able to get this very small voltage difference and amplify it, and then transmit it to a device that will be able to process it. So yes, so if we look, by the way, if you look at EMG electronic, or let's say EMG amplifier. Yep. You most of the time have this type of diagram where the thing is quite simple, where you have an amplifier and sometimes some filtering stage after. Let's see if we have something that is clearly described, so it's clear. Here, for example, you can recognize an instrumentation amplifier, then you have a low pass filter, then a follower. So yes, you have those different stage of filtering I just showed you before to process the signal. And if you want to try, you can definitely do it on a breadboard and have some nice EMG recording. So when I start thinking about this, I thought, okay, so if it's so simple, why nobody is doing something affordable and that could be used for tinkering, let's say doing some bioengineering, simple and easy and cheap bioengineering. So I think the thing is that you can have this muscle information, but if you have just one electrode, you would just have on-off information most of the time. Maybe some amplitude information, but not so much. And when you want to do some augmentation or control something precisely, it will be maybe a bit difficult just with just one electrode. And so if you need to have a 12 breadboard to get all your electronic devices, it start to be a bit cumbersome. So people have tried to design some smaller electrodes. For example, if you go to Stack Overflow to Hackaday, EMG, you will find different people doing some, as I was describing, some device that is with very simple electrodes on it. Not so much description. Look. Yeah, so you see that quite small. It's sad that it is not bigger. Yeah, but you can imagine that the person is doing some. Each of these boards are electrodes that is recording, and you can do it for really under 200 euro. Is really reachable. The difficulty is to make some let's say a clean product that is easy to use, that is modular, that doesn't require too much tinkering. And yeah, let's see if there is some other. Yeah, you can see also this pill. So here it's clearly just the amplifier. So you put some power. You have the electrodes, and you can read an amplified signal, the out signal probably here. But then after, most of the people, they use computers, and so your computer most of the time don't have an ADC, so to convert this analog signal, so you need to yourself recreate ADC, so to transform this analog signal to a digital signal that will be interpreted by the computer. And it's a lot of different challenges and all, and so I guess people haven't done this so much. So that's why I thought let's try. So yeah, so during this stream I will try to let's say design a PCB board that is trying to fit those different requirements. So I've already designed a different version of this project. So I called it CleverHand. I've designed different modules, tried different factors. So yes, that's another thing. Most of the people are trying to do bracelet, but in research, for example, since the market is mostly in research, for researcher, bracelet is not the only form factor that would be useful. It would be nice to be able to place your electrodes anywhere on the body, and to use as many electrodes as you need. If you don't want to use all the electrodes, you should not have to use them all. So here are the different requirements I put to myself, being wearable, which is really nice when you do simple experiment and you don't want to carry wires behind your participants. At least 16 channel. So since the myoband has been invented already almost 10 years ago, I think no need to recreate the same thing. So trying to upscale a bit. When you see I didn't show the meta version that is not yet released, you will have myoband EMG meta. I think they have shown some images. Let's try EMG bracelet meta. Yeah. So you can see those bracelets. They've released some nice video with this bracelet, and I think it is around 16 electrodes on it. So I thought, yeah, at least 16 channel is would be a good start. The bandwidth, so the amount of data you have, the bitrate, the rate at which you record your information is quite important. So for example, the myoband was very slow, let's say. It was 200 Hertz. So you have 200 sample of your electrical signal every second. But the thing is that you need, the rule is that you need at least 2 times the sampling rate. Your sampling rate should be at least 2 times higher than the maximum frequency you are interested in. And as I was telling you, people are using frequency in the EMG signals that are, let's say, up to 500. So reaching 1000 Hertz would be the minimum. So I fixed it to 2000 Hertz. The bit resolution might be important. I mean, this is not maybe, so it really depends on your application, the type of electrode that you use. For example, if you use dry electrodes, so electrode that you just place on the skin like this without any gel, the noise is quite important, and so having high resolution might not be very useful. But if you use gel electrodes, then you can use maybe this resolution. Something that is quite important is bipolar or monopolar. So the idea behind bipolar and monopolar is how you read your voltage information. So if you look at those different things, you could biceps, let's say. Okay, here. So here there is 2 ways to look at the voltage information. You have one electrode here, one electrode here, one electrode here. So what you could do is reading the difference, the voltage information is always between 2 points. But here you have 3 points. So you could read the voltage between this point and this one and this point, which would be called bipolar. Or you could read the voltage between this point, and this is called monopolar. So monopolar, the idea is that you have a lot of different electrodes on your skin, and you read the voltage difference only compared to one other pole. So you have this voltage, this voltage, this voltage, this voltage. While bipolar would be one signal, two signals. So bipolar is always between two other electrodes on the skin. So depending on the study, depending on the experiment, you might require both. So I thought it was important that your device let the user decide what they want. The modularity is what I was saying on the fact that you should not be required to use all the electrodes. You should be able to have smaller form factor when you need it. So I wanted to create something that is modular, affordable. I think it's quite important if you want to have high density, that each module is not so expensive. You don't want your final device to be more than let's say more than 1,000 is a bit sad in both sense. In the let's say DIY, I think it's really important if people want to redo it, that it's not so expensive. And in market aspect, if you want to sell this product, then people you should keep some margin to make some profit. Even though I think you might be able to sell this type of thing only to researcher. And open source, I thought, yeah, what I was thinking was, yeah, so there is not really any market for this, so let's make it open source. And why not, if it's working correctly, selling the devices all mounted for people that don't want to spend this time, and why not making some money out of it, but letting people do it if they want to buy themselves. So this is the idea of the system. So you have your different electrodes that are connected together via a shared bus, SPI bus, that should be able to go quite fast. They also all shared a common electrode to be able to do, as I was saying, monopolar. So they should all share a lead that is able to compare the other voltage to this lead, and a ground electrode. All those electrodes are communicating on this bus to a master board, which could be anything, could be an Arduino, could be a Teensy, could be a Raspberry Pi, anything. And you can, so first you can on this master put other extension. I changed a bit the design a little, but you could put some extension device, and you can also synchronize different, if for example 16, so if 48 channel is not enough for you, and for example you have very large surface that you want to record, or part of the body that are far away from each other, you might want to have several, let's say, group of EMG to a master, and you have another one somewhere else on your body, and you need to synchronize it to be able to be sure that all the EMG sample that you have are synchronized and shared at the same time. So here are some picture of I was able to do. So different iteration. I've done different thinking how to communicate between all the modules. So that's, let's say, the general global thing of this project. You can see concurrent viewer, 1 like. I have 1 like. Wow. Okay. Oh, ripple, nice. Okay. Okay, so that's it, and so now let's go in detail of the design process. So one thing, let's discuss about how I want to design it. Let's take a Google slide just to draw some diagram. So you would need what the way I want to do it, this new iteration, let's say, because I think I didn't share this, let's say the motivation between this project is what I was saying about having EMG, cheap, affordable EMG, but in my let's say personal objective with this was to learn a bit about electronic, about signal acquisition. So I'm continuing this project on my free time because it is teaching a lot of stuff to design your own project like this. So here, a new iteration. So what I want is my EMG, let's say, acquisition module. I want the thing that is very important is the fact that the way, so you have the electronic part, but the electrodes aspect will be very different between your usage. So you want to keep, for example, different type of since you will have different type of electrodes, you want to let it possible to connect your EMG acquisition device to different type of electrodes and make it again very modular. Let's say electrode type 1. I will make it clearer after what those different type could be, but for now let's be general. So I want the EMG acquisition to be able to be connected to different type of electrodes. And another, let's say, critical part, and I think that's what missing from a lot of EMG acquisition system, is how to synchronize and how to share all this information on a single bus and still being quite portable. So this should be another layer of let's say communication, where this module should be able then to communicate with other module. That's very pretty. Make it smaller. Yeah, I could have used Draw.io to make it look nicer. I think when I will do some cut of this stream, I will try to make a nice visualization of these different things. Okay, and you want several of them to communicate like this, and you want the another board to be able to read all of this. So head board or master, as you want, will be the one that is, so it will be the microcontroller that will read the SPI, the master SPI, that will read all the communications, and that will be able to send it to a computer. So the headboard then should be able to communicate with, for example, a computer. Could be a computer, could be a phone, anything that will maybe in the computer you will have the higher level of algorithm. So on those higher level you could have the classification, all the machine learning part, all the other models that you want on your EMG signal. You should do it on something that is a bit more powerful in terms of computation. And this communication should be you should have different way to communicate. It could be USB. It's not the best, but it's so easy and everything has it that it would be a shame not to let this opportunity. Another one that is a lot faster could be to have an Ethernet communication possible, so you can reach a very high speed of communication. So when you don't care too much about the wearable aspect, but you really need all the data, that you really need a lot of signal and to be sent quickly to the computer, then Ethernet might be a nice solution. And of course you want some wireless, so it can be Wi-Fi, Bluetooth, or anything. Okay, so that's the, let's say, global ID. I will try to make a nice diagram for the video, but that's it. So today what we are going to try to do will be thinking about this communication, this EMG acquisition, and some electrode type. In a future stream, I think I will talk more about the communication protocol, how to make the microcontroller, how to make the code for the microcontroller, how to optimize this communication and the different parameters, and again another stream, how to make the software to get all the information in an easy way, how to make a Python script out of it. So most of it I've done it with C++ for now, or C, and but of course if you want to make it accessible, you need to make it with easier languages, for example more accessible languages like Python. So I've started to design a Python version of this API, and I will try to show it in another stream. So let's focus on this and see what we can do. So I will design everything on KiCad. I used to use Eagle, the Eagle, I don't know how to pronounce. However, the fact that it's now owned by AutoCAD, Autodesk, and that there is no update, that you need to be online to use it, to connect at least and all, it was really starting to get annoying. So I decided to go to KiCad or KiCad, I don't know, and it is quite nice. To be honest, it has a lot of features, a lot of plugins, and it's quite easy to make a PCB out of it. I think most of the complaint about this software are the package manager, not this one, but when you want to integrate new footprints, when you want to integrate new symbol, it is not very intuitive, and it requires a lot of to be very clean in your folder management, and it's not optimal. Okay, so let's create a new project and call it, let's say, CleverHand. Let's start with the EMG acquisition. I will probably change the name after to make it fit my other version, but let's make it simple for now. I don't know how to write acquisition, so I will write EMG digital acquisition. Okay, here you go. So this one, so I've been searching online for a different way to do it. So you could do it let's say the hard way, with a different analog amplifier, the same I was showing you with the different you could do it this way, EMG electronics, schematic. So you use different op amp, different amplifier like this, and you end up having to make as I was telling you, what you have on your breadboard, you can put it on the PCB, and it's nice. The issue is that you also have to think about the digital to analog, analog to digital part. So it will be more work, and I was thinking maybe it's already, those type of chip already exist all packaged. So I ended up finding something that is quite cool. The series of Texas Instruments that is ADS 129X, let's say, is quite cool. I will show you this. Let's see. So you have 94, 96, 98. Depending on this number, you will have a different number of channel, and it is quite nice because you have a lot of function and features that are all integrated in this. And when you want to design something that is small, it's nice when a lot of stuff is done on single chip. You have less freedom to do whatever you want, but you can have a lot smaller package. So you can say here that you have your different input. So here you will have up to 8 bipolar input. You communicate with your microcontroller, with your head controller. You communicate with SPI bus. So that means that you acquire your signal. You do everything is done here to digitalize, so to filter and to digitalize this signal, and you can directly fetch it on SPI bus. So it's saving you a lot of trouble. It is, so for example, this one is a bit more expensive. I don't know if this shows the price here. So you see, if you buy 1,000 units, you will pay $16. But actually, if you pay for, if you want just one unit, it will be around 25-30 euro. So if you want several units, it is quite expensive. It can get quite expensive. Let me just take some water. Okay. But they have different model, and obviously the 98 is the most expensive, but it's not the cheapest. Oh, hello Tartopam. Are you still here? Maybe not. I mean, can I see the number of people? I have a screen on the side. Ooh, 3 likes. Concurrent viewer. I think only one person is viewing, so probably not here anymore. Okay. So yes, I was saying the 98 version is the most expensive. As I was telling, 28, yeah, let's say 28 euro. However, if you go to 92 with only 2 channel, or 94, it would be cheaper. The nice balance between them would be the ADS 1293, where you have 3 channel. It is a version that is a bit different in terms of architecture and all. You have different features, different possibilities, but it's less expensive. You can get, so you used to be able to get one for less than 10 euro. Now, since everything got more expensive, now I think it's around 13 euro. One nice thing is, if you look, for example, on GLC PCB, it's nice to check all the chips that you will use. It's nice to see if the manufacturer that is going to produce your chip, if they are able to assemble it directly. You could do it by yourself, but it's saving so much time and trouble. So it's nice if they are able to do it by themselves. So if you check 12, they will have different. So in stock, and let's see the stock. Oops. So you can see that they have a lot of 98, and a lot cheaper than before. So it's $20 for 98, which is getting quite affordable. And you have the 93, that is $13. so not bad. What else was the one? Oh, you have different package. Yeah, so you can see that also the size will change depending on the version that you use. Okay, so I decided to go with this one. So let's go with this model. So let's import one in your schematic. Whoops. Okay. So I think I have everything. So yeah, everything is already ordered in my custom library, so it's easier for me. So let's take this one. Up. So you can see that you have different parts. You have the let's say the communication part that is down left. You will have. Let me. Sorry. Okay. So yeah, sorry. You have the communication part on the down left side. You have the oh, sorry, I'm starting so many points. For example, this one, this schematic format is the one I prefer. Some schematic format will give you the pins more in the functional way, so it will regroup similar functionality together, while this format is a bit different. It is following the order of the pin, and I find it easier to draw your schematic with this format, because this way it is easier to start thinking how it will be placed on your board after. So yes, let's come back. So you have the down left side that is more communication, the SPI communication. You can see the SDO, SDI, the clock signal, the chip select bar. You have the analog input, all the input from the different lead that you want to measure. So what is nice with the chip is that you will be able to record an amplification of any combination of any pair of this input, which is really nice, and you can reroute this by software. So it's very convenient if you don't know exactly how you want to measure the thing and you want to do some trial, or you could do even some online trial where you record different differential voltage from different pair of electrodes online. Would be quite cool. You have a lot this section on the down right. Oh, by the way, it's down left. Okay, down left is something that is more reserved for ECG applications. So this series of controller of chip is done for EMG, EEG, and ECG. So EMG is for electromyography, EEG is for EEG. EEG is for let's try again. Let's see. EEG is for yeah, of course, electroencephalogram, and ECG is for electrocardiogram. My internet is lagging like my brain. ECG. Okay, for electrocardiogram. So this chip this chip is able to do all of this, and it has different features for it has very specific features for ECG, but we don't really care about those ones because we want EMG. Okay, so that's the main thing. So to be a bit faster, let's take some part from my previous design. So let's open KitKat on another project. Okay, so let's go CleverHand. I think. KiCad. Yeah, that's really not the up-to-date version, but doesn't matter too much. Let's take this one. Why not this one? This one. Sure. So did it close? That is not cool. Sorry. This one to be open at the same time, so it will be easier to copy paste. The interesting part. Okay, and from here, I have my. So this is, let's say, the general design of the thing. So let's be lazy and take everything, and I will describe how it is. Up. So this part is what was recommended in the datasheet to make it work easily. It is used for the for different part to be able to do some Wheatstone bridge for ECG, but in our case we just want it to not interfere with our measurement, so this is a very standard setup. Let's take another ground signal. Nope. So power, and we want the ground. TND. This one. Okay. We put it instead of the other one. Let's keep it from the ground. Up. Let's take the analog one. Sometimes you want to, so I don't know yet if I will do it, but sometimes you want to have different ground depending on the which for what they used. So for example here, since it is this ground is used to supply the chip with some power supply with to make the analog acquisition work. So you want it to be very stable and without too much noise, while the other input, which is here with VDD IO, it's for the also communication part, and this one, since it is communicating at a very high speed, it is automatically generating some noise on the source, on the power source, so it will affect the cleanness of this power source. So sometimes it's better to separate them to send, but let's see if we do it. Okay, so we have this. So with simple capacitors on the different power supply, and let's remove this one because I was thinking at first that maybe you need some termination resistor for the SPI bus, but after some test it seems that it is causing more, it is slowing down too much the communication, so it's not very good. So let's try without. Okay, I think for now we will remove this. Okay. That is, let's say, the very annoying part of this chip is the clock signal. So it is supposed to be quite well thought, because you can decide to have an onboard crystal that is that should be plugged between those two pins, and inside you have an oscillator that is making the crystal resonate, and you have some nice signal, and inside you are able to get 400k hertz frequency signal. And you have another option where you feed directly here in the clock input. You can feed a clock signal from an external source, and for example you could share between the different devices. You can share this clock input, and this one, for example, would be more, instead of having just a crystal, you would have an oscillator that would input your signal inside. The sad part is that this input is supposed to receive directly the 400k hertz, while those input require a 4 megahertz crystal. And when you look at the form factor, the 4 megahertz crystal are huge, almost 2 times the size of this chip, and the very small oscillator or crystal are for a lot higher value than this, and you find nothing almost to be able to feed your 400k here. So very sad. So I ended up deciding to use a crystal. Let's take another one. Crystal. Okay, so you have your crystal, and let's select footprint. If I remember correctly, it was, what was it? Ah, this one, I think. On the SMD version of this. There is no. Where is the SMD version of it? SMD. Let's check online. So again, GLC PCB, all component, crystal, you want the, so that's a different thing. So the one I was telling you, for the one that we will use will be crystal, while you on the other one you should use oscillator, but we will use crystal. I don't know which one I'm supposed to check. Yeah, GLC PCB part lookup table is very bad, so most of the time now I use this very nice website where you can check component. It is recording all the components they have and do a way better job at storing and being able to select different features of your components. So let's try to find crystal. So crystal, you have it here, you have it here, you have it here, you have it here. Okay, so with this we should be able to check all the crystal. Then you select your frequency, you select this one, and you keep on the active one, and you want them to be in stock at GLC PCB, and you look at which one are the most. So yeah, it's not doing a perfect job, so sometimes it's suggesting, so this is a small form factor that would be perfect. However, if you click on it, it is a crystal but for another frequency. So if you check, it will tell you that it is for you see other frequency. So nope. So we need to find the first one that is really 4 megahertz. And if you check, 8 megahertz, still not okay. Not doing a great job at filtering. Oh, here, for example. So I think that would be it. That would be the smallest. Yeah, I think when I checked, this is the footprint that you want, and you can see that it is huge compared to. I think I still have the. I don't know. You will see on the board. It is quite sad how big it is. So let's try to find this one. It's 49 SMD. 49. I have all of them, but very weird. Oh, SMD maybe. 40. Ah, here you go. So let's go for the smallest one. Okay. So we'll use this. You want it to be, oops. You want it to be in between the different input. And what is recommended is that you have the crystal input that are directly linked to capacitors that will be able to. I wasn't here at the beginning. Can you sum up what you're doing? If it doesn't just. Oh yeah, sure, of course. If you're still here. Yeah, so 3 viewers. Wow. Okay. So when did you ask? Can we see the? No, we cannot see the time. So yes. So what I'm doing, if I sum up quickly, what I'm doing is working on a project that is called CleverHand. And it is designing EMG device, so designing a board that is able to measure electrical activity on your skin from your muscles to be able to control anything from it. Let's say the sum up of it is that currently there is no affordable devices that are able to record at a lot of, let's say, medium density, so at a lot of different place on your skin. There is nothing affordable, modular and all. The first price that you will find for medium density will be around 10,000, 5,000, no, let's say 10,000 at least. And this is sad for development, for if you want to do some, let's say, bioengineering and you want to control your light with some muscle, or if you want to add some features to your smartwatch just using some finger movement or thing like this. It would be cool if everyone had access to this. And if you think about it, the researcher don't have a lot of money, and so if you want to make an experiment with EMG but you need to spend 10,000 on just a device, it's a break to your research. So I decided to try to make this device and to make it modular, affordable. You can go on my I have a GitHub page that is kind of summing these different features. At the beginning of the streams, I was talking about those different requirements that are set that I want to keep for this different module. And the idea is after to end up with kind of a chain of different modules that you can connect together and that you can put in a bracelet shape, or that you can put also on a mesh shape that you could put on the body, on garment, different. There are a lot of possibility, and I just want to make it accessible to researcher. Yeah, because there is also this idea that EMG will revolutionize the future, and that's why Meta is doing their own EMG bracelet and trying to sell it as something revolutionary. But I think we are very, very far from it, and I think for the general public, general customers, it is quite useless. So I think that's why nobody's doing it, because to make profit, to make money, it's useless. But for research, I think there is something to do. So yes, so now I'm showing how to design the EMG acquisition part. And if I have still my drawing, the idea is that the project is like this. I want to make it very modular. So I am designing this EMG acquisition board. I want this one to be connected to a communication board, and that will enable to communicate between different modules. And I want the EMG acquisition to be connected to several type of electrodes fitting the different needs. And I want everything to be very small and cheap. Okay. So let's go back to the design, the electronic design. So you have the crystal that is here, that you need to connect to the power supply via some capacitors to help filter the frequency excitation. Okay, so that's the main things that are very important on this board. And if you go in the board design, let's try, you will see the size of everything. Oh yeah, let's try. Up. So just to give you a scale, you will have, oops, let's go in edge cut here. So let's make it, we want to be small, so let's not go bigger than let's say 15. Oh, it's a bit small. Let's say not bigger, at least to start, not bigger than 30 by 30. Sorry, let's go here, up. So if you look here under on KiCad, you can see the displacement between my origin and my mouse. So the objective, we said, would be to do something that is not bigger than 3 centimeters by 3 centimeters, so 30 by 30. Okay, so you see we have a lot of space if we want to do this. So I prefer to start large to make it easy to move the component at first, and then we will try to reduce it to the maximum. If you, as a comparison, if you look at the previous design I did, for example this one, I think if I remember correctly, it's something around 16 millimeter by 25 or something like this. So we have some space. Okay, so this is the sad part. You can see that this crystal is huge compared to the rest of the component, which is very annoying, but I think you cannot really skip it. So let's keep it. Let's keep it. And okay, let's see also for the other part. What we want is to have some input. You want the let's call it con. We'll see what PCB shape we give it, but let's connect all these input, so EMG signal input to some connectors, and let's think after how we do. up. We don't really care about this for now. Just want this here, then up. Let's make it a bit cleaner, like this. We want to connect everything, and we want to give it some names. So the name are useful for PCB design after, because it's easier to understand what each track are instead of having some auto-generated names. So thank you for sending a nice project. Thank you, Nicolas Noël. Wow, so many viewers, 3 concurrent viewers. Okay, let's continue. 3, 4, 5, and 6. Okay, so what is nice is now if we go back in this and we update it, now each pins here have a understandable name, which is quite nice. Okay, so now if you think about what type of, so if I have to draw, let's go on shape. I want to show you the, let's say, the geometrical ID behind those different boards. The thing I want to do is like this. Okay, let's go. Maybe it's already, no. Take some time. Okay, so the ID. So let's imagine that if we take the example of these electrodes were very simple. My initial idea was electrodes in itself, so the wet electrodes. I don't know if you know what it looks like. I'll try to show you. Usually wet electrodes look like this, and you can buy it. You stick it. It's single use, that's the issue, but you have a very clear signal coming from it, and you can just put a connector here and connect it to your device. However, it is annoying because you need to place it. It is quite big, so you cannot have a high density of it everywhere without being all on top of each other. So that's why I thought, okay, let's try with dry electrodes. That would be reusable, and that would be easier to set. That was the big advantage of the MyoBand, is that it was dry electrodes, easy to set up. But again, let's say designing the material aspect of those electrodes, buying those metallic part that needs to be, for example, silver or gold, is another step in the process that might be expensive, that might add some cost to your device. So that's why I thought, why not using the PCB in itself? The PCB is able to provide gold-plated input, so why not using them to be electrodes directly? I am not 100% convinced that the protection layer that they are putting here is totally biocompatible. I mean, I did some tests on me. I didn't add any reaction and all. But if you wanted this to become a real product, I think you would have to care a bit more about this. And the nice aspect of it is that everything was on one board, and you didn't have to add any mechanical part to it. So cool. However, you are constrained in design because you cannot put connection from top layer to bottom layer via everywhere, because you don't want to go through those pads. So it's a lot more complicated to design. And when you have your EMG board, you are stuck with this interface, and that's one new features, or let's say requirement, that I don't want in this new iteration. So I want the EMG device to be connectable to different type of electrodes. So I want to keep this type of electrode possible, but I would like the EMG to connect to this PCB layer. So that's why I think the way I will try to do it will be the following. Sorry, let me try to find it. Okay, so let's imagine that you have your board, the current board, that would be, let's say, this is the size of the current board. Let's give it some realistic size. I think this is around the size of the current one. You give it some thickness, not thickness, 6. Okay, so let's imagine that this is your electrodes. Your electrodes will be there. Let's draw them so it will be a bit more explicit. Up. Say 2.5. I think it is 2.5. Let's give it 15. Let's connect it here, and let's duplicate it. Oops. Up, and if we replicate it, up. Right now it's 5, but let's say 6. And we want each of them to be 2.6, for example. It's a bit close. Say 3 for now. Say OK. Up, and instead of 3.3, yeah, why not? Okay, let's not spend too much time on it. And we want all of this to be your electrode, so we give it a very small thickness like this. Okay, so this is your board with your electrodes. The first iteration, you had all your EMG acquisition here, and that was constraining, yeah. So in this new iteration, what I want to do is to be able to have the new board, the EMG board, to be on top. Okay, so to be able to connect it like this. Sketch. So it's very schematic, but it's a draft ID, but that's what I have in mind. So this would be almost stuck together. This, why not the same size? Oops. Okay, and you have your EMG board here. For example, we started with 30, but it will be probably around 20. Okay, and extrude it. You have symmetrical 1.6. You have your second PCB that would be like this, and you want after to have your connection in between those two boards. And so this way, this one you can solder it to this type of electrodes, but you could solder it to other type of electrodes. which make it a bit more modular, and you're not stuck with only one type of electrodes. Oh, by the way, I didn't show you. This is the current version of the electrodes in real life, let's say. And you can see that you have the electrodes on the back, you have all the component on this, and the idea is that all of these are connected, are connectors that enable you to connect one electrode to another and in the end you have, for example, in a bracelet shape, you can have all of them connected one to another on the same bus, and you have, for example, here an Arduino that is reading from this bus. In this new format, I want the electrodes, the electrode board, to be separated from the EMG board and separated from the communication board. So this way you can create a small block of those different functionality and be a bit more modular, which is nice for research. Okay, so if this is my board, my EMG board, I need this. Where is it? I need this to be connectable to the other board, for example here, from this part. What I could do is, for example, let's say we do it very simply. So I could have, for this connection, the type of footprint I could use could be, where is it? I could use this, for example. Okay, let's do it for all of them. Up. And then that would mean F8. Up, update, close. You would end up with this type of connectors. And for example, you could put it, all of them, here. Like this, up. And then you would have to solder, if you go back here, you would have to solder those holes to those holes, and you would have your connection. So that would be the simplest way, but it's taking some space. So maybe we can do something a bit more optimal. So in GLC PCB, they offer the possibility to do how is it called? It's here. Yes, they offer to create castellated holes. Maybe you've seen that on some PCB. It's the idea that you could have half holes like this, which make it a lot easier to solder to another board. And in this, yeah. So for example, this is.
Hi, I'm Sean with part1.
So for example, they use it to connect to other board. So it's to connect board to other board. And if you look at how they do, you can see that it makes it a lot easier to solder together. So we will not be parallel. In our case, we will not have this in the same orientation, but we could think of using this type of castellated hole. I never tried with the LCPCB to do it, so I'm not 100% sure how to specify it. Let's try KiCad castellated hole. How does it work? see. Taking some time. Okay. Tac tac tac. Plate half falling board. Tac tac tac. Okay, so very easy. You just do normal hole, but on top of the cutting trays, and this way it will be understood that it is. Castellation is a matter of interpreted. Yeah, of course. So okay, so it means that I will have to double check with GLC PCB if they understood that it is castellated hole. So the idea would be to take this and move it here. If we look at the 3D shape of it, yeah, that is nice. So you have your castellated hole. So you could put this board on top of the other one. Okay. That is the input of this board, but we have also output. So the output of this board are the digital communication. So the very important pins will be this, the output of the board, the input. So you send on these pins, for example on the SDI, you send a request of which input you want to read, for example, and in the output the board will reply to your microcontroller the value of this voltage, for example. The clock signal is to make sure that the microcontroller and this board are communicating at the same pace. And one particularity of the SPI communication bus is the chip select. So every module can share these 3 pins and they can communicate on the same buses, but to be sure that they understand when they are talked to. So to be understand that the microcontroller is able to decide, I'm going to talk to this one and I'm not going to talk to the next one. To be sure that it is working, you need this chip select input, where the microcontroller will activate or deactivate these pins to say, I am talking to this one and not to the next one next to it, to the one next to it. So this one is not shared between all the board. You will see later in the communication layer how I tackled this issue, because if you think about this, it means that you have 3 wires in between all the device. That's 3, okay? But if you have 16 devices, then that would mean that you would have 3 plus the 16 of the chip select of each of them, which is a lot, and you don't want big cable or super large cable, and you don't want all of them to have fixed address, etc. So let's discuss about this on the communication layer design. But in any case, you need this output part in the board. RMB, I think for now we will not care about this one. So I will have to check on the data on the documentation, but I think we can just let it like this. We might have to connect it to the ground or to the power supply, but we will see. Data ready, same, we don't care. And I think, and yeah, obviously, let's think. Maybe one thing that we want is also to have, so let's imagine that we use the same. We don't want them to be the same. Oh, yeah, it's fine. Okay. And so we want one for the SDO. We want one for the SDI. we want one for the clock, and we want one for the chip select. That's for sure. So at least 4 are very important. The rest, we might have to think about this, but one thing that might be important is to have one output that is also an input. So let's say that this pin 6 could be shared between other modules. This way, it's for the monopolar reading of the EMG signal. This way you can read your skin voltage in comparison to a shared common point somewhere else on the body. Okay, so you would have this. I think that is, let's say, the minimal number of input and output. Okay, if we go back here, if we do that, up, up. Put it here, for example. Okay, here we go. One very good thing with this let's say design structure, so by that I mean if we put it in this position, that means that we can use this side but also this side, so both sides are free to be used, which means that this one, for example, this very annoying huge crystal could be put on the back, which is cool because it's saving a lot of space. You could have all of this here, and then it means also that you can reduce the size drastically like this. Let's try to minimize like this, keep some space, but trying to start to constrain a bit the device. Up. Okay, maybe one thing that we can do in case we forget something, let's try to take this. It's sad because they are not in the right angle compared to the one from below. Up. We will have to change them again after, but for now let's try just simply like this. In general, since I really care about the size, most of the time I remove all the name, let's say, of the component. If you need to place the component by hand, then you will need to use a schematic on the side to know which value, etc. So in general, I find for this very small board, I think having the label of each component is not the most useful. So for now, I will remove them all. Up, a bit cleaner. So we have this. So right now I'm using 0402 component. We could go smaller and use 0201, but for example for GLC PCB manufacturing it is a lot more expensive, so we don't need to go this small, and we can do a lot already with just this. Okay, so let's put this one maybe in the right orientation to make it in front of the footprint. Okay, so we have in 1, in 2, oops, it's not in the right order, in 3, in 6, in 4, up. Okay, then we'll move it, we'll be able to make it very close. Let's not care about this one for now. Let's care just about the front side. Okay. Then what we want is to have our decoupling capacitors to be close to our power supply input. We want this probably on the same side. So this one, that was the thing I was telling you about, having the names. It's quite nice because I know directly this is the capacitors, the decoupling capacitors of the crystal. Oops. Here. And those one. So what I wanted was, oh yeah, I wanted to be sure that install is fine. Just want to change this, but later. Okay. So this and this, those two guys, we want them on the back. Let them on the back. Okay. This one. So again, this one are the component for the electrocardiogram features of the chip that we don't care. So we put them just to have a standard functioning way without thinking too much. We just use the one prescribed by the datasheet documentation. Up. So we have three guys like this. Oop. Let's put a smaller grid. Noise. We can move it up. Again, this one is for the decoupling of the communication, let's say, communication power supply. This one is for the analog power supply. We might need to have some other, because here the one I'm using are for the very standard one, but maybe I might add after another side here with yeah, maybe I can do it directly. I have to think. Yeah, let's see later. Okay, this one, okay. CVREF. This is what the datasheet is suggesting. And this one is another not very useful one for us, like this. Okay. And yes, another thing I was going to say is one thing that you might want to try to do every time is to keep standard spacing between your different throw pins. So the standard one is 2.5.4. So let's put up. I need to put the origin here. That's what I was doing. Okay, so 143, 120. Each user. Okay, grid origin 149. Already forgot. 143, 120. Okay, so if we have this, normally this guy, yeah. So if we want to have standard spacing, we might want to have this one stuck together like this. So by standard, what I mean is that in most of the cases you will have small connector like this, some pins, and the very, very, very standard spacing between all of these pins are 2.54 centimeters. or millimeters, because it is 0.1 inch. So if you want to use this board for something that is standard and use this type of connector, it will be easier for you. So let's keep this close together, up. Then you want to do the same here. Doesn't really matter here, like this. Let's put it in the right order for this to be directly in front. Oops. Okay. Okay, and this one will be here. Okay. This one, let's put it here then. Okay. And because we never know, let's add another one for nothing right now, just so in case we need to connect something, it might be quite nice. Oops. Okay, and this way it is how do we say, symmetrical, the number of pad. Okay, let's go back in this unit. Okay, we want it to be not too far. This one, we can get it closer. So you see the size of the board has been reduced quite a lot already, because we have we don't have a lot on it, so that's normal. Okay, something like this. This we should not forget, like this. We should not forget our backside. Backside will be just the crystal. Something like this. Something like this. Let's find a better way, a better position, better. Okay, and if you look at the 3D design, you have something that is very small, a very small module like this that you will be able to put on your different electrodes and connect to your communication layer. So okay, so I will just get some water. Okay, so I think that's the ID, the global ID with this, and let's remove those two. Okay, then yes. Okay, then we will have to do the routing, but no need. I think it's important to have the global ID working first, trying to see if everything fits together before trying to do the routing, because the routing can take some time and be tricky sometimes, so better to do it when you are sure of what you're doing. Okay, so here you can see that we still have some space. we still have a lot of space here. So we could use this space for different purpose. For example, one thing that could be added would be to have directly, one thing I just forgot. Obviously what you need, what type of input you need for your microcontroller or for your chip is power supply, of course. So you need at least a ground and 3 volt or 5 volt, something like this. So let's say that yeah, I think what we will do is that the bus will share 5 volt, just something that is powerful enough, not very filtered, but just at least 5 volt that is able to be provided to the whole to all the devices, and use power converter to transform this 5 volt in something smoother for the 5 volt here and for 3.3 volt from here. So this will have to be added, and this is something that we can add here. And maybe one thing that we want for our electrodes will be also a ground. That might be useful to have a ground. Oops. Here, okay, and if we import it, okay, so we have our 5 volt, our ground, which one it is, G14, G15, those two for the top, and this one for the bottom. Okay, so we want to go back to the standard spacing. Hop. Here we go. Same here. We need to put it at the right horizontal position first, and then space it correctly. Which side do we put it? Maybe the other side would be easier. Okay, so we have this like this. This we move. We need to increase the size of the board, and since we have one more, let's add one unused one in case for later. Here, for example. Okay. So we have this. So what is the size? Right now we are the stream can be accessed again from the managed list. No, is it? Okay. Okay, yes. So the size right now is 2 centimeters by 1 centimeter. So you see, we're still very small. So it should be fine for now. I think I will have to, in another stream, I will work on the power supply part. And yeah, I think power supply. Then we will work on the oops, where is it? So I think we wrap here for today. So let's sum up. So what we just designed is a first draft of this EMG acquisition part. For next time, we will try to add to this part the power supply converter. We will try to design a simple version of this electrode of one electrode type, maybe two if we have time. We will try to do the communication layer, where I will try to speak about the strategy I decided to use for the selection, the chip select selection. Chip select selection. So to decrease the number of pins and wires needed to communicate with 16 module. And yeah, and we will see from there where we're going. Okay, thank you for my lovely viewers, and see you soon. Bye bye.